In the name of Almighty God, I'm Mahsa Sankoshi, and today I want to talk about dark matter density distribution. The first subsection would be 2.2.1 galactic dark matter density functions. We review now the galactic dark matter density distribution, or ROI, often considered as the most plausible in the literature. All the profiles assume spherical symmetry, which reduce the radial coordinate measured from the galactic center. The functions are listed in Table 2.1 and plotted in the Figure 2.3 for plausible values of their free parameters radius s, rho s, and alpha inst. Some of these functions can be conveniently recast in terms of a collective formula, which three parameters alpha, beta, and gamma also refers to as the double power law formula. Here we want to review alpha, beta, gamma. Rho alpha, beta, gamma reduced is equal to rho s divided by r divided by rs to the power of gamma bracket 1 plus r divided by rs to the power of alpha and all the bracket to the power of beta minus gamma divided by alpha. And we have a matrices at the nfw where the alpha value is 1, beta is 3, and gamma is 1. GNFW, that alpha is 1, beta is 3, and gamma is gamma. And the chord is thermal, the alpha is 2, beta is 2, and gamma is 0. The possible detection of dark matter subhollow with mass of few 10 to the power of 7 in a region of the Milky Way near the Sun is claiming the reference 62. The author employed high precision pulsars timing to reconstruct the acceleration of several pulsars, finding that these accelerations appear to be directed toward a region where the observed visible matter alone cannot account for the required gravitational pull. Now, Table 2.1 describes the plausible spherical density profiles ρr for dark matter hollow in galaxies. And when we have a NFW, rho NFW R is equal to rho RS multiplied by RS divided by R multiplied by 1 plus R divided by RS to the power of minus 2, and generalize NFW. Rho G NFW R is equal to rho S multiplied by RS divided by R to the power of gamma multiplied by 1 plus R divided by RS to the power of gamma minus 3. And rho Einstein is r is equal to rho s exponential minus 2 divided by alpha Einstein multiplied by brackets r divided by rs to the power of alpha Einstein minus 1. And chord isothermal, rho is r is equal to rho s divided by 1 plus r divided by r is to the power of 2. And Burkert, rho Burkert r is equal to rho s divided by 1 plus r divided by rs multiplied by 1 plus r divided by rs to the power of 2. The parameter alpha, beta, and gamma control the shape of the dark matter density profile at different radial distances from the galactic center. Specifically, alpha controls the sharpness of the transition between the inner and outer slopes. Beta affects the outer slope, and gamma determines the inner slope of the profile. These functions are motivated by the following considerations: the Navarro, Frank, and White NFW profiles is the most common benchmark choice motivated by the embodied simulations. The density diverges as r to the power of minus 1 close to the GC, and the version with two parameters fixed alpha is equal to 1, beta is equal to 3, and gamma taken as a free parameter in the notation of equation 2.10 is sometimes called the generalized NFW, which is a Noah Frank white, and the GNFW, the gravitational Noah Frank and white profile. When the gamma is greater than 1, the slope at the center is steeper than for the standard NFW. In this case, the profile is referred to as the contracted NFW, CNFW. For instance, this had been proposed by Moore and collaborators, who found gamma is equal to 1.16. Such contracted profiles emerged in some early numerical simulations which included baryons. The Einstein profile emerged as a better fit to more recent numerical simulations. Loosely speaking, the Einstein profile density is more chubby than NFW. More precisely, the Einstein power law exponent continuously changes, which are reduced as controlled by the shape parameter alpha Einstein. The value alpha Einstein is equal to 0.70, represents a reasonable average over the different values suggested by different n-body simulations. The next one is chord profiles, such as the chord truncated is a thermal profile based on the reference 47, or the Burckhardt profile based on the reference 48, feature a constant central density. They have been motivated by some observations of galactic rotation curves that may be pointing toward the presence of a core. See, for example, the reference 49, and by numerical simulations finding that the effect of baryon feedback lowers the central density. For example, the reference 50. Cintio and his colleagues in 2014, based on the reference 51, suggested a profile which has the double power law from in equation 2.10, but with parameters alpha, beta, gamma that are not the same across all galaxies, but rather depend on the stellar to hollow mass ratio of each galaxy. The dark matter profile is then effectively ranged from cusp the two chord ones, adapting to the stellar and the dark matter content of each galaxy. This is based on the results of simulations that include baryons as discussed in section 8.1.1. In some of the considered profiles are diverged as r tends to 0. However, in all cases, r to the power of 2 rho r tends to 0 unless gamma is unrealistically large, such that the central region of the galaxy contains just a small amount of dark matter. The fact that at face value embodied numerical simulations differ from observations is known as the cusp-core problem, and it is discussed more thoroughly in section 8.5.1. So here figure 2.3 illustrates dark matter profiles, figure left and table right, the corresponding parameters in the parameterization of the profiles in table 2.1. They produce the procedures to determine the parameters of the each thermal profile is different from the other ones. See the text for details. In the table, we provide RS, row S to 2 and 3 significant digits, a precision sufficient for more computations. Still more precise inputs are needed in specific cases, such as to precisely reproduce the J factors discussed in section 6.2 for small angular regions around the galactic center. So we have a galactocentric R in KPC in x-axis, and in y-axis we have a raw dark matter in gigaelectron volt per cubic centimeter. So as you are watching, whenever the galactocentric radius is increasing, the density is decreasing. While the various density profiles give similar results at distance larger than a few kpc from the GC, including around the location of the Earth, they do differ considerably. By orders of the magnitudes, at smaller distances close to the GC, there are no observational data on dark matter profile. Moreover, the resolution of numerical simulations doesn't allow to go blue, say a fraction of kpc. The behavior of rho r is thus simply governed by the assumed asymptotical functional from as r tends to zero. As a consequence, indirect dark matter signals from the inner galaxy, such as gamma ray fluxes from regions a few degrees around the GC depends strongly on the uncertain dark matter profile. This is in contrast to many other dark matter signals, which depends on the dark matter profiles away from the GC. Dark matter dark detection signals depend on the dark matter density at the position of the Earth. A number of dark matter signals probe the local galactic neighborhood. For example, the fluxes of the high energy positrons produced at most a few kpc away from the Earth, as well as dark matter signals that probes regions distant from the GC, for example, gamma rays from high latitudes. The next chapter is 2.2.2, determination of the Milky Way parameters. Next one has to determine the parameters RS typical scales reduced and rho S typical scales density that enters in the tentative dark matter distributions rho R. This can be done in the different ways, for example, by extracting their values from numerical simulations of Milky Way like hollows, or determining them in some way from observations of the Milky Way or similar outer galaxies. One approach is to impose that the dark matter profiles for the Milky Way satisfy the following set of the constraints. The density of dark matter at the location of Sun. This quantity was studied by many groups using a number of different techniques, notably the global method of fitting the entire rotation care of the galaxies, as discussed above, or the local methods which relies on the studying local stellar kinematics, especially the stellar motions in the vertical direction to determine the local gravitational pull and therefore the local dark matter density. The global method can provide a precise determination of rho but is sensitive to the uncertain modeling of the baryonic components of the galaxies. The local methods are the less precise and suffer no one hand from the systematic due to peculiar local conditions such as asymmetries in the north and south galactic hemispheres, and on the other hand, from the simplifications in the analysis, for example, whether or not the so-called tilt term, which correlates radial and vertical stellar motions, is included. So we have a table 2.2, which is describing dark matter density at the location of the sun. The top set consists of the historical studies. The bottom set contains a selection of works published after the release of Gaia data, although not necessarily using them. The middle set lists selected results of the latest, for example, 15 years ago. Note that the position of the sun may not be exactly the same for all others, that the methods are different, that the key assumptions might differ, and that the relative renormalizations might be necessary based on the references in the 52. So you're seeing the first category uncertainty of about a factor of 2 between 1986 until 1991, and another is Einstein and Navarro, Frank White, and also isothermal stellar traces, non-isothermal stellar traces between 2008 until 2017, and the results depends on the chosen tracers, stage, and systems errors on determinations. Average of recent results infrared 2 sigma range from simulations is between 2018 until 2022. The recent determination of rho in towards the rho is equal to rho r is equal to 0.40 giga electron volt per cubic centimeter, which is equal to 0.0106 m per PC to the power 3. The typical associated errors is about the tolerance positive negative 0.10 electron-volt a cubic centimeter, but possible spread up to the 0.2 have bidirectional to the 0.8 giga-electron-volt per cubic centimeter, sometimes referred to as a factor of 2, is often adopted, as is evident from the selected results listed in the table 2.2. Different determinations are still in poor agreement. Historically, the conventional value used in the literature since the 1990s used to be rho is equal to 0.3 gigaelectron-volt per cubic centimeter. This value increased following several studies performed mostly between 2009 and 2011, which found somewhat higher central values. Other studies, on the other hand, found smaller central values. Additionally, the associated error remained a topic of intense debate. Data from the Gaia mission stimulated new activities aimed at determining rho, but the situation is not yet settled, and a more precise determination of rho seems difficult to achieve. For comparison, the total matter density, including normal matter, average over a neighborhood of a few hundred parsecs around the location of the Sun, is estimated to be an order of magnitude larger than the dark matter density. We have a 4.5 gigaelectron-volt per cubic centimeter, and which is equal to 0.120 m to the per p to c to the power of 3. Equation 2.11 means that the mass of the dark matter included within the orbit of the Neptunes, which is equal to 30 AU, is of the order of the 10 to the power of minus 13, or equivalently that the mass of the Sun corresponds to the mass of all of the dark matter contained in a sphere of radius 2.8 pc is equal to 9.2 Ly, comparable to the distance to the nearest star about 4 Ly. This illustrates how dark matter is largely self-dominate locally. One may wonder whether its presence in the solar system could nevertheless be detected via its influence on the orbits of planets and closely mentioned asteroids. For one, the accumulated dark matter would slightly increase the effective mass of the Sun as seen by the outer bodies. However, direct astronomical observations, while accurate, are still not particularly constraining. The resulting bound on dark matter density in the solar system is rho is less than 5,000 gigaelectron-volt per cubic centimeter, which is about 15,000 times larger than the expected density. In other words, dark matter has no significant effect on the orbits of the planets in the solar system. A related issue is whether the average value for rho in equation 2.11 can be modified significantly by the presence of the astrophysical bodies in the solar system. For example, whether it could get increased by the gravitational attraction of the Sun or decreased by slingshot effects acting on dark matter particles passing the planets, and notably Jupiter, but also Venus and the Earth itself, in the same way as what happens for conventional asteroids. Any appreciable modification of local dark matter density and speed distributions would be particularly important for the interpretations of dark matter direct detection results. See Chapter 5, and for predicting the neutrino flux from dark matter particles captured in the Sun or the Earth. See Section 6.9. A series of detailed studies identified a number of subtle effects that, for the most part, cancel each other out, leading to the particularly negligible net effect, at least for dark matter particles that interact only weakly with the astrophysical bodies. Note also that the energy density in dark matter is rho is equal to 20 kilowatt per square meter, about 14 times higher than the power density of the sun's radiation and the surface of the earth. Good to keep in mind just in case this energy someday turns out to be in a usable form, converting our universe into one giant battery pack. The total dark matter mass contained in the Milky Way, this quantity was also studied by many groups using different techniques. The methods include the study of the kinematics of bright satellites such as the dwarf galaxies or Magellanic Clouds, the kinematic of stellar streams, the escape velocity of nearby rogue stars, and the use of various tracers. For M200 to the power of dark matter, the mass of the dark matter contained inside the water reduced R200 defined in section 2.1.2 below equation 2.3. We will use the standard value Ma200 to the power of dark matter is equal to 1 positive negative 0.25 multiplied by 10 to the power of 12. However, it is worth noting that the advent of the Gaia mission and its precise astrometric data resulted in a lot of activity recently, with a number of studies in 2023 arriving at a factor of a few lower value for the Ma200 dark matter. For the Milky Way, the radius 200 is equal to 200 to 300 kpc. Hence, one can think of Ma200 dark matter as the total dark matter mass contained in a large sphere of radius 200 kpc centered around the center of the galaxy. For comparison, the stellar massive rate with similar techniques is about h multiplied by 10 to the power of 10, and the distance from the Earth to the large Magellanic Cloud is about 48.5 kpc, imposing the constraints 2.11 and 2.13 fixes the RS and ROS parameters for the Navarro, Frank, White, Einstein, and Booker profiles in Table 2.1. For the thermal profile, however, no solution can be found that would simultaneously satisfy both constraints that r to the power of minus 2 behavior of dark matter density as larger r or radius is too slow and always results in Ma200 dark matter larger than the value in equation 2.413. For this profile, we therefore disregard the constraint in equation 2.13. Instead, we set a radius Rs is equal to 4 kpc. For this profile, we therefore disregarded the constraint in equation 2.13. Instead, we set radius S is equal to 4 kpc as was done in the original literature, and then determine the value of the rho s for which the constraint on the local density in equation 2.11 satisfies. The results of these procedures are presented in figure 2.3, where we also plot the resulting profiles. The values of the parameters determined with this procedure and presented here in general don't differ much, at most by 20% from the parameter values often used in the literature. The next literature would be 2.3 dwarf galaxies. The Milky Way is surrounded by a number of satellite galaxies, for example, astrophysical systems that are tied to the main Milky Way halo by gravitational attraction. Apart from the large and small Magellanic Clouds, which are big enough to be seen with a naked eye, the large majority of the satellites consist of the dwarf galaxies. Most of these are the dwarf spherical type, and only a few are dwarf irregulars. Historically, sculptor was the first one to be discovered in 1938, and it is often considered as the prototypical the DSPH, which is the dwarf spheroidal. Seven more dwarf galaxies, Fornax, Leo 1, Leo 2, or some minor Draco, Carina, and sextants were discovered up to the 1990. Collectively, these eight dwarf galaxies are referred to as classical. With the advent of the digital surveys such as ASD, SS, and the Subaru Hyper Super camera, which covered the northern sky, Pan stars disk, which covered the southern sky, and the Gaia operating from the space. Many more dwarfs have been discovered. These are referred to as ultra-faint. The current total stands just short of 50, including several whose nature and properties are not yet confirmed. See the table 2.3. The list is probably going to increase as the surveys becomes more sensitive and cover larger portions of the sky, for example, with upcoming Rubin's Observatory, formerly known as LSST. There is also the Sagittarius DS spherical, discovered in 1994, which is nearby and larger but stands apart since it is believed to be tidally disrupted by the Milky Way halo. So there is a footnote here, footnote 12. We should stress that the different parameters discussed in these sections, rho, r, and ma200, which is density, radius, and mass, and later on the rotational velocity of the sun, are interconnected and correlated. As discussed above, they are typically determined within a global galactic model, which consists of the baryonic components, but often also requires to specify dark matter density distribution and the dark matter velocity distribution. Hence, strictly speaking, using the values density, radius, and M200 dark matter to constrain the dark matter distribution is inconsistent. However, the impact of the choice of the dark matter distributions on the global model is limited. Thus, the procedure can be considered as valid for all current practical purposes. The Shu and his colleagues in 2023 claimed a discovery of the first dark matter-dominated dwarf galaxy external to the Milky Way system's fast J0139 plus 4338 is a very large dwarf galaxy located at about 29 MPC, which is found to have a dark matter dominated ratio of total mass versus baryonic mass 47 positive negative 27. So you are seeing this table, which is describing table 2.3, describing most of the discovered of spheroidal satellite galaxy of the Milky Way. Data are from many different sources. For example, references 58 and 59 are not necessarily with homogeneous methods. The tau DSV and the DSV factors are defined in equation 6.8. D is proportional to the dwarf's mass due to the dark matter and are computed for a 0.5 degrees disk. The cases with particularly large variations in the iteration Omicron 10 in the center value are labeled with a star. The values in parentheses are estimates. So if you are watching that, the classical's name, the confirmed ultra faint names, and also the candidate's name. So I want to read at least the name and the discovery years. Sculptor in 1938. So the energy is about 18.20 gigaelectron volt per centimeter. Another name is fornax, low 1, low 2, Ursa Minor, Draco, Carina, and Sextans and Sagittarius in 1994. Wheelman 1, Ursa Major 1, Ursa Major 2, 2001 and 6, Butes 1, Canis Venatici 1 and 2, and Coma Berenices, Hercules Low 4, Segu 1, Low T, Low V, and Segu 2, Sagittarius 2, Reticulum 2, Eridanus 2, Tucano 2, Horologium 1, and Phoenix 2, Tucano 4, Aquarius 2, Crater 2, Carina 2, Carina 3, Antilia 2, Pegasus 4, and Virgo 2, Bootes 5, Low minor 1. And the candidates are Triangulum 2, Draco 2, Pictor 1, Greece 1, Greece 2, Tacona 3, Colombo 1, and Reticulum 3, and Tucana 5, Indus 2, and Cetus 2, Virgo 1, Cetus 3, Bootes 4, and Centaurus 1, and Eridanius 4. And the last candidate's name is Ursa Major 3. So you see that we have a lot of uh, dwarf galaxies in the at least Milky Way. So the definition of the dwarf category is not clear-cut. For example, there are no universally accepted ranges of values of the mass, size, and luminosity of a small galaxy that would define it as being of the dwarf type. In general, one can think of a dwarf galaxy as having a dark matter-dominated mass around the dark dwarf type. In general, one can think of a dwarf galaxy as having a dark matter-dominated mass of around 10 to the power of 6 m. See figure 3.1, where the actual dwarf galaxies can differ by a couple of orders of magnitude from this value. For instance, a fornax is estimated at 56 multiplied by 10 to the power of 6, while Segu 2 at 0.23 multiplied by 10 to the power of 6. The half-light radius, or a half-light, defined as the radius of the circle that contains half of the light emission from the galaxy, can be from a few tens of parsecs to several hundreds parsecs, according to simulations. The viral radius 200 of the dark matter halo of the dwarf galaxy tends to be one order of magnitude bigger than the radius half light. Based on the reference 61, the number of stars identified as belonging to the dwarf galaxy can be as low as dozen or as many as several thousands. Dwarf galaxies are a promising targets for dark matter search because they contain only a few stars and are believed to be dominated by dark matter. The likely reason is that the dwarf galaxies constitute relatively shallow potential wells compared to large galaxies, facilitating the explosion of baryonic gas by early supernova. While the subsequent star formation rate is low, the estimated mass to light ratio, m total divided by L, can be of the order of several tens m divided by L. Sculptors 200 m divided by L, for example, Draco, and can even reach a few thousands m divided by L, for example, Sago 1. The large dark matter content of dwarf is, of course, good news for the expected intensity of the dark matter signals. Moreover, the scarcity of stars and other active astrophysical objects implies that the signal is less contaminated by foreground emissions compared to the other systems. However, this comes at the price of having only a small number of tracers with which one can reconstruct the dark matter content and the dark matter density profile. Also, these tracers are typically only stars, no hydrogen clouds, such as those that crucially helped in tracing the rotation curve of spiral galaxies in sections 1.1 are found in these systems because of the stellar phase and complex dynamic. The determination of dark matter density functions in the dwarf sphericals are challenging and subject to intense debate. For example, observationally, there appears to be not consensus in the literature on whether the stellar kinematical data point to a Cosby or to core dark matter distribution. Number of measurements, especially in early 2000s, had suggested the preference for a core in the centers of the dwarf spherical. Subsequent observations showed, at least in the specific cases such as Sculptor and a few others, that a scope Navarro Frank wide profile also fits the data well. The results of numerical simulations, on the other hand, seem to support the formation of cores for middle-sized dwarf, while low-mass dwarfs appears to develop cusps consistent with the trends discussed in section 1.3.2. The core versus cusp nature of dwarf galaxies might also depend on the history of star formation. Dwarfs that stopped forming stars more than 6 giga-years ago developed cusps by unimpeded contraction, while those that kept forming stars have had their dark matter content heated by stellar bursts and have thus developed cores. A common practical approach in the literature involves using the profile like those discussed in section 2.2, with parameters determining number of different ways. For example, the Geringer Smith in 2015 the reference to 59. From this one, then predicts the corresponding dark matter signal sections, um, next sections. So thank you so much for watching my tutorial video until the end. And if there is any literature for this, if any simulation for this literature, you can find it from github.com/pass script slash Kashi script and slash Safra script. Today is 18th of August 2026.